Okay, before we start today, talking about Gauss's law, there are a couple things that I want to go over from chapter 21 and the beginning of chapter 22 that are going to be important as we go forward. One is just, we never really talked about the units of electric field as a physical quantity. If we go back to how we defined the idea of electric field, we said that a charged particle creates some kind of electric field in space, and another charge Q sits in that field, and the force on charge Q is equal to its charge times the electric field. And I should be careful and draw these as vector equations. That means that electric field as a physical quantity has to have units of a force per unit charge. So the units of electric field that we'll be using for now are newtons per coulomb. There will be another electric field unit that we'll see next week, I think, when we talk about electrical potentials. But in order to do that, we have to understand another unit of electrical potential called the volt. So electric fields can be in newtons per coulomb. They can also be in volts per meter, which we will understand better when we talk about potentials and voltage. The other thing that we didn't really talk about when we did chapter 21, which I guess we started before break even, is the difference between insulating materials and conducting materials. I think everybody knows from middle school science what the difference between an insulator and a conductor is. In a conductor, electrical charges are free to move, so electrons can move around. In an insulator, they are not. Which is why, if you think about a wire in your house that connects your television to the wall or your computer to the outlet, inside that wire is something conductive like copper. Around the outside is something that's an insulator like rubber, and so when you grab that wire, the electrical current doesn't flow through your hand because electrical charge is not free to move through an insulating material. The reasons for why some materials are conductors and some materials are non-conductors are talked about briefly in your book in the beginning of chapter 21. It has to do with the fact that in a metal there are conduction band electrons that are kind of free to hop between the atoms. We're not going to get into the sort of material science level of that. We will simply take it for granted that there are insulating materials and conducting materials, and for the purposes of finding electric fields in and around objects, we need to know one important fact about that, which is in a non-conductor, electrical charges are not free to move. So if we put excess charge on an insulating sphere, or in an insulating sphere, for example, that charge can be distributed throughout the volume of the object. And so this whole thing will have a volume charge density. We use a rho for volume charge density, charge per unit volume. That is not necessarily uniform, because I could put an excess of positive charge over here, and those positive charge aren't free to move because it's insulator. I could put an excess of negative charges over here, and those negative charges are not free to move in the insulator. So a non-conducting sphere can have charges distributed throughout its volume, and that charge distribution does not need to be uniform. In a conductor, on the other hand, if I put, say, two positive charges inside this conductor, they are free to move, and because they exert a repulsive force on one another, they will move as far away from one another as they can get, which means if I put an excess of electrical charges inside a conductor, those electrical charges will move to the surface of that conductor. So at equilibrium, if none of the charges are moving, and we're always assuming during these chapters on electrostatics that the electrical charges are not moving, at equilibrium, the electrical charge of a conductor resides on the surface. So we can write that the surface charge density of this conductor is some charge per unit area. And in most cases, we can assume that that charge density is uniform, because if I were to put, say, an excess of positive charges on this side of the sphere, they would have a greater repulsive force between them than these charges, and they would be pushed away from one another until the charge distribution was sort of equalized across the surface of the sphere, of the conductor. So in a conductor at equilibrium, the charge in the interior, okay, in the volume of the sphere is 0, and all that charge lives on the surface. And again, that'll be important for a couple of the problems that we do, or several of the problems we do in this chapter on Gauss's law, so that we can know, if we look at a particular region of an object, where there is charge and when there is not charge. So before we go any further and talk about Gauss's law, we have to define yet another physics term that has to do with fields, and that is the idea of flux. It kind of helps to think about electric fields almost like, well, there's a couple ways to think about it. Remember we said that in physics we treat these fields as if they're real things, and in fact, in some sense we treat the field lines as if they are real things. So you can think about electrical flux as the number of field lines that pass through a particular surface. So flux is the amount of electrical field passing through a surface. If the surface and the field are perpendicular to one another, if I've just got, say, a rectangular surface with some electric field passing through it, and if the electric field is just constant across that area, then the flux, and we use a capital phi for the flux, is just equal to the magnitude of the electric field times the area. That is not always the case. In some situations, you might have an electric field and a surface which are not perpendicular to one another. So here we've drawn a picture of a surface, and the surface normal, the perpendicular to that surface, is this vector A, and the electric field is passing through that surface at an angle. So if we want to know the flux through that surface, we have to take not just the product of these two quantities, but the dot product of these two vectors. So the flux of the electrical field through the surface is the dot product of the direction of the electrical field and the direction of the surface. And for the direction of the surface, remember in physics we always use that normal vector. What that means is, for example, if you've got an electric field like this, pointing in the y direction, let's say, and you've got a surface like this, okay, imagine a piece of paper laying flat like so. It's hard to draw on this tablet. Okay, let me color that in. And that's our area. The flux through that surface is 0. You can almost think of the electric field lines as being like flowing water and the areas being like a net. Because the surface normal of the surface points that way and the electric field points that way, E dot A is equal to 0 because the surface and the normal, the electric field and the normal to the surface are perpendicular to one another. So there's the maximum flux when the electric field goes through the surface like that. There's a minimum flux when the electric field goes through the surface like that. That leads us to the technical definition of electrical flux, which is that the flux through a surface is equal to the integral of the electric field over the area. Why integral? Because you can imagine a situation where the electric field, say we take a surface A, the electric field is not constant over that surface. The electric field is bigger on parts of that surface than others, in which case it's not a simple matter of multiplying the electric field times the area. You have to integrate the contributions of the electric field over each little element of the area. So the definition of flux, the complete technical definition of flux, is that flux is the integral of the electric field over the area. And flux is not a term that's unique to electric field. You can talk about magnetic flux. You can talk about the flux of a fluid through a surface. This integral of the vector quantity over the area is a very common type of quantity that you'll encounter in physics. So if, for example, we look at a situation where there's a very complicated surface and a very complicated electric field, notice that the electric field isn't constant. Okay, the lines are closer together in some places than others. The electric field is not always perpendicular to the surface. It's perpendicular here, but it's not perpendicular there. And the surface normal is constantly changing direction because the surface is not a simple shape. It's this kind of complicated curve in space. So actually doing this integral could involve a changing electric field, a changing direction of the normal to the surface, and a changing relationship between these quantities. So actually calculating the flux of the electric field through a surface could be really, really complicated. And as we'll see when we talk about Gauss's law, we're going to sidestep that complication by only dealing with situations where the electric field is relatively simple and constant, and the symmetry of the surface lends itself to an integral that we can actually do. One thing to notice about the flux through a surface is if that surface is a closed surface, in other words, a closed three-dimensional surface, and if all the sources of the electric field, all the electric field lines start outside the surface, that every electric field line that goes into the surface on this side comes out of the surface on the other side. And we can prove mathematically, although we will not do that in this class, that if there are no electric field lines that start on the inside, if all the electric field lines pass through starting from the outside, that the flux through this surface, as we have it drawn here, the electrical flux through that surface is equal to 0. Here, the electric field is in the opposite direction of the area, right? The electric field is going this way. The normal to the surface is pointing outward. So that dot product gives us a negative sign. Here on the other side, the flux lines are coming, or the field lines are coming out of the surface. That gives us a positive sign to the flux. So on this side of the surface, there's negative flux. On this side of the surface, there's positive flux. And the total flux through that surface adds up to 0. That is the case for any surface that does not enclose any electrical charges. If there's no electrical charges in here, that means there will be no field lines that start from the inside of the surface. And again, we're talking about these field lines as if they're real things, which is kind of weird, but that's kind of the way you talk about it. So this is equal to 0 if there's no charge inside the surface. What if there is charge inside the surface? If there is charge inside the surface, then that gives us Gauss's law. Gauss's law says that if there is some kind of electrical charge inside of a closed surface, and that's what this little closed surface integral means, that the integral of the electric field over that area is equal to the charge enclosed divided by epsilon 0, that permittivity of free space, that electrical constant from Coulomb's law. So Gauss's law says that the flux through any closed surface is equal to the charge enclosed by that surface divided by epsilon naught. That is true of any electric field, that is true of any charge distribution, and that is true of any surface. This fact is always true. If you look at this drawing from the book, down here, it shows us two surfaces, a green surface and a blue surface, and a charge Q sort of located at the origin, and it draws the field lines of that Q coming out. It is true that if we were to integrate the electric field over this blue surface, okay, the electric field at every point in space passing through this surface. Notice that the electric field isn't constant everywhere on the surface because some places on the surface are further from this charge than others. Notice that the electric field vector and the normal vector to the surface are not always parallel to one another because the surface has a complicated curvy shape that does not correspond to a square or a sphere or something with a constant perpendicular direction. Nonetheless, if we were to do this integral, if we were to add up the flux through every point on this closed surface, and integrate it over this whole complicated curved surface, let's call it S, we would find that that integral is equal to the amount of charge enclosed in the surface, Q, divided by epsilon 0. That integral, in general, is not easy to do. Gauss's law is always true, but actually performing that integral for an arbitrary surface in an arbitrary electric field can be anywhere between complicated and impossible. If we took the green surface, though, if we take this sphere, notice that a sphere is always the same distance from this point Q. Notice also that the normal to a sphere is always radially away from the origin, and the electric field of a point charge is also always radially away from the origin. So some shapes and some charge distributions will lend themselves to easier integrals that can actually be done. We can actually use Gauss's law to calculate some things. If we choose a surface and a charge distribution that lend themselves to actually being able to do this integral. For example, let's look at just a point charge at the origin, charge Q, surrounded by a sphere of radius r. And let's write down Gauss's law for the surface of that sphere. What is the integral of E, the electric field, dot dA over the surface of that sphere? Well, Gauss's law says it's Q, the charge enclosed by the sphere, divided by epsilon naught. Okay? Let's see if we can actually do this integral, though. What do we know? Nothing yet about the electric field, but we know something about the relationship between the electric field and the area. One, we know that the electric field is constant everywhere on this sphere. How do we know that? Because the symmetry of the situation dictates that any way you look at this point charge at the origin, no matter where you put your vantage point out here, it looks the same. So the electric field cannot be a function of theta or phi, the angles in spherical coordinates. The electric field is just a function of r. And if the electric field is just a function of r, got my head in the way there. If the electric field is just a function of r, that means it has to be constant everywhere on the surface of that sphere. So if the electric field is constant everywhere on the surface of that sphere, then I can just pull it. Well, actually, there's one more thing I have to take care of, which is the dot product. We can also tell from the symmetry of the situation that the electric field has to be radially out from the origin. Okay? If the electric field is radially out from the origin and the normal vector of a sphere is radially out from the origin, then the electric field is always perpendicular to A. So E dot dA is just equal to E dA. Okay? We don't have to worry about that dot product if those vectors are always perpendicular. That means I can write my integral here. The integral of E dot dA is equal to the integral of E dA, and that's equal to the charge over epsilon naught. And since the electric field is just a function of the radius and is the same everywhere on that sphere, I can just write this as E times the integral of dA is equal to Q over epsilon naught. And the integral of dA is just the area of the sphere. The electric field is constant. It doesn't participate in the integration at all. So what I've got is E times the integral of dA over the surface of the sphere is just 4 pi r squared. And that, according to Gauss's law, is equal to Q over epsilon 0. And if I solve that for the electric field, I get that the electric field is equal to 1 over 4 pi epsilon 0 q over r squared, which is exactly what we already know the electric field of a point charge to be from Coulomb's law. So we haven't discovered anything new here. What we've done is use Gauss's law to confirm Coulomb's law. That Gauss's law is at the very least consistent with this expression for the electric field of a point charge. So go over that example in the book a couple of times until you understand it, until you understand these arguments here about the symmetry of the electric field, the symmetry of the surface, and how they allow you to simplify the integration. This brings up an interesting point, which is Gauss's law happens to be a true law of physics, but we can ask the question, is it actually a useful law of physics? Can you actually do anything with it if, in most cases, the surface that you might be interested in is too complicated to actually do this integral over? If the relationship between E and dA is constantly changing and constantly complicated, this is not an integral that you could actually ever reasonably do, which means we can only use Gauss's law to find the electric field in situations where there's a high degree of symmetry and where the electric field is constant over some area. Which kind of means we can only use Gauss's law to find the electric field in situations where we can kind of look at the field and guess what shape it has and what relationship it has to the distance. So Gauss's law is a little bit useful. We'll use it to find the electric field of a line, which we kind of already done, a plane, which we've kind of started doing in chapter 21. But the fact that Gauss's law is actually a general statement about all fields is actually something that's really, really important. I should mention before we end this video that Gauss's law for electromagnetism is just an example of a more general mathematical statement called the divergence theorem. Those of you who took or are taking Calc 3 may have encountered the divergence theorem. It says that if we take the surface integral of some vector field over a closed surface, that is equal to the volume integral of something called the divergence. And the divergence is a vector operator. It's something you can calculate about a vector field. Gauss's law for a general field looks something like this, that the integral of the field dotted with the surface normal integrated over that closed surface, so this is like the integral of E dot dA, okay, in our specific example, is equal to the volume integral of this thing called the divergence, which is a measure of how much a vector field is diverging from a point. And one of Maxwell's equations actually says that the divergence of the electric field is equal to Q over epsilon naught. So as you go into more advanced versions of electromagnetism, the kind of E&M course you might take as maybe a second semester sophomore physics major or first semester junior physics major, you will see Gauss's law in a more general form used for more sophisticated expressions of electromagnetism. But one of the reasons that Gauss's law is also sometimes referred to as Gauss's theorem is that it is a statement of pure mathematics. It holds for any vector field. And this mathematical version of Gauss's theorem, which makes no specific reference to electric fields, is true of any vector field no matter what it is. So what we'll do in the next videos is we'll look at a couple of examples of how to use Gauss's law to calculate the electric field of some simple objects and compare those results to the results we got of finding the electric field directly by integrating the electric field over space. Okay, so yeah, so I'll go ahead and stop this video there, and we'll look at some examples next.